Thank you to Jean-Michel for inviting me to present my solution to this challenge. So in this challenge, we're given an RF recording of some signals, and we're told that we have 7 radio emitters transmitting. 6 of them like GPS signals, and the 7th one doesn't. So basically, we're asked a number of questions which are intended to guide us to the answer. And the goal of the challenge is we're given some signals of an unknown description. We know that they are inspired in GPS, and we have to decode some data embedded in those signals. So let's get started. When trying to visualize or analyze data, I often work into a Jupyter notebook. So in fact, the report for my solution is just a notebook. I've done things in GNU Radio and also in Spectrum. So let's actually go and look at the signal in Spectrum. I have a screenshot of the waterfall here, but I have also in Spectrum running. So if we look at the signal in Spectrum, we can see some bursts of data, and it's quite wideband data, like a couple megahertz wide. So that looks like the GPS kind of signal we're expecting. We can see the carrier frequency of the signal, and that actually solves one of the easiest questions in the challenge, which is in what amateur radio band these people are transmitting. Since we have here 3 something megahertz, and the LO offset for the recorder is 25 megahertz, we already see that they are transmitting in 28 megahertz in the 10-meter band. Something else we can do in Spectrum is this phase plot, which is added like add phase plot. And if I zoom in all the way in, we can already see that this is BPSK data. So we have this slant curve because the tuning here is not 100% correct. But other than that, we see these 180 degrees phase changes. So that already tells us that the signal is BPSK. That's basically the same as GPS. So if we try to do something which actually works for GPS, and it's like this. If we have a CDMA signal like GPS, especially for the case of GPS, where we have several PRN repetitions per data symbol, that kind of signal is going to have many spectral lines. And in those spectral lines, you can actually read the data. So you can read the data directly without having to demodulate the PRN. And that's very useful. Unfortunately, if we try to zoom in here all the way in, and we zoom, we don't see these spectral lines. And here I'm at the limit of the FFT given by in Spectrum. But if we go and do things in GNU Radio, like extracting a slice of the signal and then going further through in Spectrum, we don't see any spectral lines. So that would have been a good shortcut to solve this challenge, but it doesn't work for reasons we'll see. So then, since we know this is a BPSK modulated signal and it has a lot of SNR, we see here that the signal is quite strong. It's above the noise floor, so we can demodulate it without the knowledge of the PRN or anything. So let's go on, let's write a GNU Radio flow graph which does BPSK demodulation. That's a basic exercise, and this is what my flow graph looks like. I have the recording here. This is to bring the signal down to baseband, Costas loop for carrier phase recovery, then the symbol synchronization. And in here, I'm using the chip rate, which is given in the challenge description. But this is something you can check yourself. If you multiply the signal and the conjugate, the complex conjugate of the signal delayed by one sample, you can see a spectral line at exactly the chip rate. So that's where this number comes from, actually. So with the knowledge of the chip rate, we can use symbol sync to recover the clock. and then with complex to real we can obtain the symbols. There are a number of additional filters in this flow graph, which are some GUI things to see the signal running in real time. And also, for reasons we'll see, we are storing in a file the average frequency of the Costas loop, and also the power of the signal, the average power. So I'm actually going to present my solution in the order I did things, which is not typically the order you present them later. The first thing, I went directly to look at this BPSK demodulated data. I wanted to see if I could just figure out what kind of PRNs or CDMA or GPS-like modulation was used. So here I plot the BPSK symbols obtained in the GNU Radio flow graph, and we see here two bursts of data like we saw in Spectrum, but there is something a little bit weird. If we zoom in to just the first burst of the data, we see that we have +1 symbols, -1 symbols, but we also have 0 symbols, which is really strange because a BPSK signal usually wouldn't have anything in the middle. So anyway, if we zoom in, we actually see that there are zeros in the signal. So we have +1, 0, -1, 0, 0, etc. That is very weird and will play a major role in what is about to come. Something else which I usually do with a symbol stream is to find the autocorrelation. With the autocorrelation, we can start seeing patterns in the data. If there are headers or repeat instructors, these will typically show up in the autocorrelation. So if we compute and plot the autocorrelation of this BPSK stream, we can see that we have many peaks. These peaks correspond to repeating filters in the data. So this can actually help us gain more information about the signal. If we zoom in to the central portion of this plot, we see that the peaks are at very precise locations, 2046, 4096, etc. These are actually multiples of 1023, and in fact we can see here a very tiny peak at 1023. So actually all the integer multiples of 1023 appear in this autocorrelation plot. What is so special about 1023? Well, that's the length of a PRN of GPS. So since the challenge description speaks about GPS, we think we're on the good track and try to exploit that. And now I have to explain a sidetrack which I tried to follow to demodulate this data, and in the end it didn't work, but bear with me for a moment. So we know that this data, actually let's go back to this BPSK data. We know that there are repetitions of 1023 symbols, so we can divide it in blocks, and there are actually like 60, on the order of 60 different blocks in this data. Then we can try to compare each of the blocks, and we see that they are different. So there is some cross correlation between each of the different blocks, but it is not like +1 or -1. We see that there is some similarity, but there is also some variation. What this tells is that, well, we have 6 different speakers which like GPS signals. So probably they are transmitting sometimes, and sometimes they are not transmitting. And here the idea I have, which turned out to be wrong, was, okay, if we have this +1, 0, and -1, maybe there are 2 speakers transmitting at the same time. So when they transmit the same, we get +2 and -2. When they transmit an opposite symbol, we get 0. So with that idea, I tried to push it forward, and what I considered was the covariance matrix of all these repetitions. The covariance matrix is a linear algebra tool which we can use to find out how many vectors, linear vectors, are involved in some data. And actually this matrix will tell us that we have essentially 6 vectors involved, which is good because we have 6 speakers. But it was very difficult to try to figure out what 2 speakers at a time were transmitting, because the vectors which appeared in each of the blocks kept changing, and actually it was quite confusing approach and it didn't work very well. So in the end, I dropped it and figured out I could try something else. So when you get stuck, it's good to go move and do something else. So there's another question already, which is, what is the seventh speaker about? We're told he doesn't like GPS. So my idea was that maybe there was a narrowband signal hidden somewhere. I couldn't find it in Spectrum. If we look at in Spectrum, there isn't anything. These spurs are from the recording or the transmitted device. So there isn't anything. I also consider the possibility that it could be buried under the main CDMA signal, so that only when you were able to decode the CDMA, you could subtract it and then access the data. But that would be a little bit hard. So then something you can do is to actually zoom out, both literally and figurative, and see that the length of the bursts is different. So why is it different? Maybe there's something special about it. And that's the reason why my GNU Radio flow graph has a measurement of the signal power into a file. So if we plot that file, we have the signal power over the whole 13 seconds or so that the recording lasts. And we see here some pattern. It looks like ZipW, but it isn't CW or Morse code, because the length of the dits and das is different. We have here something very short, something mid-range, something long. If we look at these two patterns, we can lay them on top of each other, and we see that they are exactly the same. And we can try to look at this in more detail, and it actually looks like ASK, so amplitude shift keying, or actually on-off keying, where a 1 is transmitted by the presence of a carrier and a 0 is transmitted by the absence of a carrier. And it's quite easy to go and pick out the symbols. For this, you need to derive the clock frequency and clock phase by hand, but you can easily do it. It's just a matter of drawing dots and checking proportions. So we see 1 0 0 0 1 0 0, etc., etc. And then I looked at this for a while, and when you have some binary data, there are a large number of possibilities. First, you need to wonder if your data is differentially encoded or not. Then it might be ASCII, so you're looking for printable ASCII characters. It might be another thing, such as Baudot. Baudot is very popular with amateur radio RTTY, so that could be something. It could be Varicode, which is used in PSK31. And I tried all those things and didn't make any progress. So we'll come to that later, because I decided to go and take another look at this CDMA data. So let's go back to the CDMA data, and it is very useful to go and look many times at the description of a challenge like this, because there are some details that you might have missed. And here there is a sentence which is key to the solution. It says that all the gold codes are too complex and simpler coding schemes are best suited for the exchanges. So gold codes is the kind of PRNs used in GPS. And the way I was trying to approach the CDMA decoding was like a blind test, like not knowing the PRN. For example, if the challenge designer had chosen completely random PRNs, that would be the only way to go about it, and it would be hard. So there is also something psychological about these kind of challenges. The solution needs to be something that is reasonable for someone to find and achieve. So let's actually think about this. By simpler coding schemes, it might refer to a linear fit shift register, which is actually the building block for gold codes, and it's the easiest way to build a deterministic PRN. An LFSR looks like this. It's a shift register with some XOR tabs, and to generate a 1023 chip sequence, we actually need only 10 cells in the shift register, and then we need to choose the positions where to place these XOR gates or tabs. Now we need something about mathematics. So there's a way to encode these positions as a polynomial, And all the different LFSRs that you can build to generate a 1023 symbol sequence are given by something called primitive polynomials. I won't explain what primitive polynomials are, but the good thing is that there is a list of primitive polynomials in the internet. For example, in this online encyclopedia of integer sequences. And the list is not so long. So for degree 10, we only have 60 polynomials. So the thing we can do is grab that list from the internet, generate our 1023 bit sequences following this LFSR algorithm, and then correlate each of those 60 different sequences with the data. That's what I did. And if I plot the results, if I plot the correlations of each of the actually 100 different blocks in the first burst, we see that most of the 60 PRNs we tried yield very small correlations, but some of them yield good correlations. And actually there are 6 different PRNs giving good correlations here, which is very promising because we are expecting to see 6 different speakers. Then we can look at those LFSRs, which give good correlation. They are defined by these polynomials. And we can plot the correlation. And I mean the correlation with its sign. So we can determine if the data transmitted is +1 or -1. And we see these 6 sequences, which are BPSK data, basically something changing +1, -1, etc., etc. And sometimes they match, sometimes they don't match. What does this have to do with the original data, which is ones, zeros, and -1s? This is something I had always in the back of my mind were trying to crack this, which is something called majority voting. This is sometimes used in GNSS to multiplex several signals. Majority voting is just you have, let's say, 6 signals. Some of them are +1, some of them are -1. So we look at the majority, and so you decide the value of your signal. If there's a tie, usually what you do is to break the tie with some random decision or some deterministic decision. But you would like to break ties often because you don't want zeros in your BPSK stream. That has to do with amplification of BPSK. But in this case, what I thought is, well, maybe there's no tie break at all. So if there's a tie, then we put a 0. And if there's some winner, we put either +1 or -1. And it's not necessary to understand this to complete the challenge. But what I did was to reconstruct all this sequence, assuming this majority voting, my 6 PRN sequences and the data sequences I had here. And I reconstructed a symbol sequence like so, and compared it with the original data. So there is some slight misalignment here because I haven't been careful to align the data, but otherwise most of the symbols match. So that's the way we can find the description for our signal. Moving on, we have these symbol sequences, and we can take a look at them. And actually, it's quite useful to plot them. Here I'm already revealing the trick because if you know that there are patterns in the data, you can plot them like a matrix, like left to right and top to bottom, and you'll see patterns. For example, here this column is always the same. Here these columns are always the same. So what's the trick here to see these patterns? Again, it's autocorrelation. And this is something that occurred to me to try when I had these sequences. So actually the way I think the challenge is framed is for this on-off keying data of the 7th speaker to serve as a clue for the CDMA data of the GPS-like signals, but I actually only find when I had all the ingredients combined. So if we look at the autocorrelation either of this on-off keying sequence or of the 6 GPS-like speakers data, we see some peaks at delays multiple of 10 and also more multiples. So if we plot the data as 10 columns in a matrix, we see some patterns, and anytime you see blocks of 10, that's a hint for UART. So UART uses often 10 bits because it embeds 8 bits into 10 bits using a start bit and a stop bit. It looks like so. So here we have the start bit, we have 8 bits, and something important is that this is least significant bit first, so that's confusing sometimes, and then we have the stop bit. In the challenge, there is a variation of this UART because the start bit is high and the stop bit is low. You can consider sometimes that there can be variations because the designer decided to do so, or just because of small mistakes, so you need to cope with those. When we accept that maybe this data is UART with this high instead of low and this low instead of high, we can take the good data, which would be ASCII, and here the most significant bit is low because these are printable characters. And we see that the message here is hello. So, well, that's awesome. Let's try to pull this trick with the CDMA data. So when we go to the CDMA data, we have the same, we have these matrices here in blocks of 10 bits, and when we plot the ASCII data here, we see buongiorno, bonjour, buenos dias, zdravo, guten tag, and seonke. So those are greetings in different European languages, which actually makes a lot of sense if we go again and read the challenge messages exchange which countries. So by looking at those languages, we can make out what countries the speakers come from, and Google is quite helpful for those. So the countries are Italy, France, Spain, a number of Slavic countries which have the same kind of greeting, Germany of course, and actually seon okay means it's okay in Finnish, so go figure. What else have we missed? Another small question in the statement of the challenge is what is the exact carrier frequency offset of the transmitting usurp and the recording oscilloscope? And for that, what I did was to output the Kostap's loop frequency, and we can plot that Kostap's loop frequency, and we see the frequency quite close to 230 hertz, actually 229.8. So that's the fine frequency offset. And that's basically it. So the trick here was mainly about noticing that these are LFSRs and trying to brute force matching of the 60 possibilities, and also noticing that the data uses UART framing. Once you have those ingredients, it's pretty much done. So now I would be live and happy to answer questions from the audience.